A movie of every atom in a shattered glass, filmed with perfect precision, would not look illegal if it were played backward. The glass would rise from the floor, the cracks would sew themselves shut, the sound wave would collapse back into silence, and every molecule of air would return exactly the energy it had taken. Nothing in Newton's equation, force equals mass times acceleration, forbids that film. Nothing in Maxwell's equations forbids it. Even ordinary quantum evolution does not announce that one direction of time is real, and the other is impossible, and yet you have never seen it happen. That is the problem. Not that time moves forward, that is experience. The problem is that the deepest equations we use to describe matter usually do not contain the command that experience obeys. They do not say break, but never unbreak. They do not say remember yesterday, but never tomorrow. They do not say hot coffee must cool, lungs must exhale, stars must burn fuel, batteries must die. At the microscopic level, the machinery can often run either way. At the human level, it never does. The first layer is not mystical. It is thermal. Put a drop of ink into a glass of water. At the beginning, the ink is concentrated in one small region. After a few minutes, it spreads until the water is faintly colored everywhere. The ordinary explanation is diffusion. Molecules of ink are knocked around by water molecules, and because the impacts are random, the ink wanders outward. That explanation is correct. It is also incomplete, because the same collisions, if their velocities were reversed exactly, would make the ink gather itself back into the drop. The reason it does not gather is not that the reverse motion violates mechanics. The reason is that the reverse motion requires a state of absurd precision. Here is the simplest calculation. Suppose a box is divided into two halves, left and right, and there are 100 gas molecules inside. If the molecules are spread randomly, each molecule has a 1/2 chance of being on the left side at any instant. The chance that all 100 molecules are on the left side at the same time is 1/2 multiplied by itself 100 times. In spoken form, that is 2 to the minus 100. Numerically, it is about 7.9 times 10 to the minus 31. That is already small, but 100 molecules is not a gas. A mole of gas contains Avogadro's number of molecules, approximately 6.02214076 times 10 to the 23. For a mole of gas to crowd spontaneously into half the box, the probability is 2 to the minus 6.02214076 times 10 to the 23. The law has not forbidden it, probability has buried it. This is what entropy measures, not disorder as a mood, not chaos as a metaphor. Entropy counts how many microscopic arrangements correspond to the same visible condition. Ludwig Boltzmann wrote the relation in the form S equals K sub B times the natural logarithm of Ws is entropy, measured in joules per Kelvin. W is the number of microscopic states that look the same from the outside. K sub B is Boltzmann's constant, exactly 1.380649 times 10 to the minus 23 joules per Kelvin. The equation says something severe. A macrostate is what you see. The gas fills the box. The coffee is warm. The glass is broken. The ink is spread. A microstate is the exact position and momentum of every atom. Low entropy means very few microstates give the same appearance. High entropy means an enormous number of microstates give the same appearance. The world goes from low entropy to high entropy because there are overwhelmingly more ways to be high entropy, not because the atoms know the future. That sentence sounds ordinary. It is the arrow of time. But this is only the first layer of the problem. Probability explains why entropy increase is typical. It does not yet explain why the past was low entropy in the first place. If all the microscopic laws are reversible, then a high entropy present usually has a high entropy past, as well as a high entropy future. A scrambled state almost always comes from another scrambled state. If you see ink evenly mixed in water and you are given no other information, the most probable history is not that it began as a neat drop. The most probable history is that it was already mixed. So the second law of thermodynamics depends on a boundary condition. The observable universe began in a state of extraordinarily low entropy. This is where the physics stops being intuitive and becomes exact. In 1872, Boltzmann tried to derive irreversible behavior from collisions in a gas. He introduced a quantity called h, written as the integral of f times log f over velocity space, where f is the distribution function of molecular velocities. His h theorem showed that, under the assumption called molecular chaos, h decreases with time. Since entropy is essentially negative h, entropy increases. The result looked like a derivation of the second law from mechanics. Then Joseph Loschmidt objected. If the mechanical laws are reversible, then for every gas state evolving toward equilibrium, there must be another state with all velocities reversed that evolves away from equilibrium. The same collisions, reversed, decrease entropy. Boltzmann had not derived a one-way law from a two-way law. He had inserted an assumption about typical initial conditions. That objection exposed the heart of the problem. Ernst Zermelo sharpened it in 1896 using Poincaré recurrence. In a finite mechanical system with fixed energy, the system should, after a sufficiently long time, return arbitrarily close to its earlier state. Not soon. Not on any useful human timescale, but in principle. If recurrence is possible, entropy cannot be an absolute staircase that only climbs forever. The second law must be statistical. Boltzmann's mature answer was probability. Entropy decrease is possible in the same sense that all the air in a room could move to one corner. The equations permit it. The waiting time mocks it. Now follow that down into the equations. Newton's equation is second order in time. If a set of particles follows a path, then the same path with all velocities reversed is also a solution, provided the forces depend only on positions. Hamilton's equations say it more sharply. The time derivative of q is the partial derivative of h with respect to p. The time derivative of p is minus the partial derivative of h with respect to q. Q is position, p is momentum, h is the Hamiltonian, total energy function. Reverse p and reverse t, and the structure survives. Classical mechanics does not care which end of the movie you call the beginning. Electromagnetism is mostly the same. Maxwell's equations, with electric fields and magnetic fields transformed properly under time reversal, do not explain why radio waves spread outward from an antenna instead of converging inward from the universe to shake the antenna in just the right way. The outward wave is not more legal than the inward wave. It is more natural. Because the initial condition was simple, the inward wave would require the surrounding electromagnetic field to be coordinated in advance. Again, the arrow hides in the boundary condition. Quantum mechanics does not rescue common sense. The Schrödinger equation says I(h bar times the time derivative of psi equals h pi. At h bar is Planck's constant divided by 2 pi, approximately 1.054571817 times 10 to the minus 34 joule seconds. SI is the quantum state, h is the Hamiltonian operator. In ordinary isolated quantum evolution, the state changes unitarily, which means information is not destroyed. A perfect quantum evolution can be reversed by applying the inverse unitary operation. That is not philosophy. Quantum computers depend on it. The apparent irreversibility enters when a system becomes entangled with its environment. A particle in a clean superposition interacts with air molecules, photons, dust, thermal radiation, the measuring device, the observer's retina. The phase relations that made the superposition visible are not destroyed in the total wave function. They are dispersed into correlations too numerous to track. This process is called decoherence. Makes quantum possibilities look classical, because interference has spread into the environment. Nothing fundamental has vanished. The information has moved into degrees of freedom you cannot collect. This is also why memory points one way. A memory is not a ghostly possession of the mind, it is a physical record. Synaptic strengths, molecular configurations, written ink, magnetic domains, charges in a transistor, pixels, scars. To make a record, a system must become correlated with another system. To keep the record stable, unwanted alternatives are dumped into the environment as heat. Rolf Landauer made the connection precise at IBM in 1961. Logical irreversibility is tied to physical irreversibility. Erasing one bit of information costs at least k sub bt, log 2 of dissipated heat. At room temperature, say 300 Kelvin, that energy is k sub b times 300 times the natural logarithm of 2, about 2.87 times 10 to the minus 21 joules per bit. That is the Landauer limit. A memory of the past is possible because the past left records. A memory of the future is not possible because the future has not yet left records. The asymmetry of memory is not added to physics by consciousness. Consciousness inherits it from thermodynamics. The brain is warm. It burns chemical-free energy. It exports heat. Every remembered face, every sentence understood, every decision made is embedded in an irreversible metabolism. The mind does not float above the arrow of time. It rides on it. Now the difficult calibration. There are places in fundamental physics where time reversal symmetry is not perfect. This matters because the phrase physics says time should not move forward is only mostly true. The microscopic laws of classical mechanics, electromagnetism, and much ordinary quantum physics are time reversal symmetric. But the weak nuclear interaction contains violations of discrete symmetries. In 1964, James Cronin and Val Fitch at Brookhaven National Laboratory studied neutral K mesons, or kaons. The long-lived neutral kaon was expected to decay into 3 pions, not 2, if CP symmetry were exact. CP means charge conjugation and parity, replace matter with antimatter, and reflect space like a mirror. Cronin and Fitch sent kaons down a 17-meter beamline. They found 45 2-pion decays among 22,700 decay events. That was about 1 event in 500. It was small, it was decisive. CP symmetry was not exact. If CPT symmetry holds, and in local relativistic quantum field theory it is one of the deepest structural results, then CP violation implies T violation. T is time reversal. So nature does contain a microscopic distinction between time forward and time backward in weak interactions. In 2012, the Babar collaboration at SLAC reported a direct observation of time reversal violation in neutral B mesons using 468 million B and anti-B pairs produced in epsilon 4's decays. That result is real. It is not why coffee cools. The weak interaction arrow is tiny, specialized and measured in particle decays. The thermodynamic arrow governs gases, bodies, machines, planets, stars, memory, aging, and every ordinary, irreversible event. A kaon decay can distinguish T from minus T. It does not put a broken glass back together. The everyday arrow of time is not mainly written in the weak force. It is written in the statistical structure of many particle systems and in the low entropy boundary condition of the universe. Feynman would not let the label become the explanation. In the Feynman lectures, he treated the distinction between past and future with his usual refusal to pretend that words solve the problem. He emphasized that if we could see all the individual molecules in enough detail, the reversed microscopic movie would not look like a violation of physics. At the large scale, an egg splattering is plainly irreversible. At the atomic scale, the laws do not carry the same obvious arrow. The gap between those two descriptions is the work. He also framed entropy not as a mystical increase of disorder, but as a loss of available energy. When things at different temperatures are left alone, they tend to become the same temperature. The useful difference disappears. Hot stove and cold ice become lukewarm surroundings. Mechanical work becomes heat. Organized motion becomes molecular agitation. The energy is still conserved. Its usefulness is not. That is the exact place where time gets its teeth. The universe does not mark energy as useful or wasted. We do. But the distinction is physically measurable. Free energy is the part of energy that can be converted into work under given conditions. Entropy measures the dispersal that reduces that possibility. For a reversible heat transfer, ds equals dq over T. ds is the change in entropy. dq is the heat transferred. T is absolute temperature in Kelvin. For irreversible processes, the entropy of the total isolated system increases. There is the everyday future, the direction in which free energy becomes less available. A living organism looks like an exception only if you draw the boundary too tightly. A body builds proteins, repairs cells, stores memories, pumps ions, grows ordered tissue. Locally, entropy can decrease. Globally, the body consumes low entropy chemical energy from food and oxygen and releases higher entropy heat and waste. Life is not a rebellion against the second law. Life is one of the ways the second law operates in a universe with energy gradients. Now go back farther. The remaining problem is why the universe had free energy to spend at all. The early universe was hot and nearly uniform. The cosmic microwave background today is a nearly perfect blackbody radiation field, with a temperature about 2.725 Kelvin. Its temperature variations across the sky are only about 1 part in 100,000. Uniformity sounds like high entropy, and for ordinary gas in a box it is. But with gravity, uniformity is special. Gravity makes clumping natural. A smooth distribution of matter in an expanding universe has low gravitational entropy compared with a universe full of black holes. This is the cosmological root of the arrow. The early universe was not low entropy in every simple sense. It was hot, dense, and close to thermal equilibrium in its radiation, but gravitationally, it was extraordinarily ordered. That special condition allowed matter to clump into galaxies, stars, planets, chemical gradients, and eventually organisms capable of making records. Without that low gravitational entropy beginning, there would be no usable arrow to ride. This is sometimes called the past hypothesis, the assumption that the universe began in a very special low entropy macrostate. It is what makes the second law point the same way everywhere we look. Your coffee cools in the same temporal direction in which stars burn. in which memories form, in which fossils accumulate, in which radiation streams outward from galaxies, because all these arrows trace back to the same asymmetric boundary condition. The equations describe possible histories. The boundary condition selects the history we inhabit. A local miracle is not enough. The whole environment has to cooperate. That is the part popular explanations often miss. They say entropy increases because systems become disordered. But a shattered glass is not merely disordered. It is correlated with the room. It has left records in the floor, the air, the light, your nervous system. To reverse it, the correlations must reverse. The universe must become a conspiracy of precision. The fundamental laws do not say no. The state of the universe says no, with a probability so overwhelming that it becomes the practical meaning of impossibility. Feynman's way of thinking cuts through the fog here. Do not ask what time feels like. Ask what minimal physical system contains the arrow. A gas expanding into a box contains it. A hot object cooling in a cold room contains it. A bit being erased contains it. A measurement becoming a record contains it. In each case, the same structure appears. Many microscopic states correspond to the later condition, fewer to the earlier condition, and the universe began in a condition that made the earlier one available. The convergence is not coincidence. The thermodynamic arrow, the radiation arrow, the memory arrow, the biological arrow, and the causal arrow are not separate arrows pasted onto time. They are different faces of the same statistical fact. Entropy was lower in what we call the past. Physical records formed as entropy increased. Organisms evolved to exploit records. Brains named the record-rich direction past and the not yet recorded direction future. So time does not move forward because a cosmic clock pushes it. The equations do not contain a little engine labeled flow. In relativity, time is a coordinate woven with space into spacetime. In quantum mechanics, time usually enters as a parameter in the evolution of a state. In thermodynamics, time acquires a direction because the states of matter are not evenly arranged across possibility. The universe is moving from special to typical. That is the phrase. Special to typical. A low entropy state is special because it requires constraints. The ink must be gathered. The glass must be intact. The coffee must be hotter than the room. The star must contain nuclear fuel out of equilibrium. The brain must maintain delicate electrochemical gradients. Remove the constraints, and the system explores the larger region of possible states. It does not know it is becoming disordered. It is simply going where almost all the states are. Forward is the name we give to that direction. The philosophical consequence is not that time is an illusion. That phrase usually hides more than it explains. The consequence is sharper. The flow of time is not a fundamental force added to the laws. It is the experience of irreversible record formation inside a universe with a low entropy past. You feel time passing because your brain is a dissipative physical system, continually updating records while exporting heat. You cannot step outside the arrow to inspect it, because inspection is itself an arrow-making process. The observer is not outside the experiment. The glass still does not rise. The coffee still does not heat itself from the room. The forgotten bit does not restore itself without a physical trace. But the reason is subtler than physics forbids it. The reason is that physics permits too much. It permits both directions at the microscopic level, and then the statistical weight of many-particle reality crushes one direction out of experience. The universe does not need a law that says time moves forward. It only needs a beginning that was special.